Hello, everyone. Welcome to Monday. Okay, so today we are going to continue what we're doing with series, although I want to say a little bit about sequences because I can tell from the exam some people were a little bit confused. And so let's take care of that issue. All right, so let's talk a little bit just briefly for a moment. I'll get a new sheet. And I just want to say something about some of the problems on the exam, because it's clear that some of the students don't actually know what's the difference between a sequence and a series. So the sequence, as we talked about, I said, is a list. So this is a list of numbers, or a list of numbers or terms. Let's call it a list of terms. So it looks like A1, comma, A2, comma, A3, comma, all the way up to AN, and it keeps going. And we can determine whether or not the sequence has a limit. So to determine whether or not this sequence has a limit, we look at the limit as n approaches infinity of the nth term. If you get some number, a fixed number like L, okay, and it's less than infinity, it's finite number, then that happens to be your limit. If it's oscillating back and forth between two numbers, if it's blowing up to infinity, then it's not a convergent sequence, and so you won't have a limit. So we want to look at sequences that converge and sequences that diverge. So sequences that converge will give you that they are approaching a number, one fixed number, and sequences that diverge either go to infinity or you can't find the actual limit of the sequence. So in the quiz, in the exam, the first thing was you had to identify what this sequence looked like. So this sequence AN, and I did tell you N started at 1 to infinity. And this sequence was 1, comma, 1/3, comma, 1 over 9, comma, 1 over 27, etc. And so again, you have to be able to identify the pattern. And so as I'm looking at this, this looks like 1 over 3 to the 0, 1 over 3 to the 1, 1 over 3 squared, 1 over 3 cubed, 1 over 3 to the 4th. Now this is the first term, A1, and then, let me see, I need to, okay. And this is the second term, A2, this is the third term, A3, and this is the fourth term, A4. So I can see for each N, so for each value of N, the term before it, that particular term is N minus 1. So as I'm looking at this, it looks to me like the nth term is going to be 1 over 3 to the n minus 1, which we can write as 1/3 to the n minus 1. Now, some of you try to sum this. There's no sum. It's just a sequence, just a list of terms. Okay, so Bn, same thing, starting at 1 was 2 minus 3/2 plus 4/3 minus 5/4. And so if I were to write this sequence, I would look at this as 2 over 1, comma, minus 3 over 2, then positive 4 over 3, minus 5 over 4. So here again, this is A1, A2. I'm sorry, these are B's. B1, B2, etc. And so now for B1, I see I get 2 over 1. For B2, I get 3 over 2. So whatever the n is, Bn, it looks like the n is on the bottom and n plus 1 is on the top. And then I can see that this thing oscillates back and forth. So I'm going to need a minus 1. And is it to the n or is it to the n minus 1? Well, when n is 1, I want it to be positive. So therefore, I would do that. Okay, Where I was very concerned was people didn't know the difference between the sequence and the series. So a series is a sum of terms, not a list. And we've been looking at particular series tests to determine whether you can actually sum up all of these terms and actually get a finite number S. Okay, so when we talk about whether or not a sequence converges, then we're looking at whether or not the terms start to look like something. When we talk about whether a series converges, we're talking about, can you actually get a finite number for the sum? Or in other cases, can you look at the limit as n approaches infinity of the nth partial sum? Okay. So again, I can go over some of the limits of series and sequences during office hours. What I do want to get to now in module 7 are the comparison tests. So let's review for a moment. The first thing we had was the geometric series. And on the test or any type of assessment, you have to be able to tell the test you're using, whether or not the series converges or diverges, and give justification. So if the problem is worth 10 points, you may get 3 points for knowing the test, 3 points for saying it converges or diverges, and 4 points for whatever you using the test to prove that it converges or diverges. So for the geometric series, we have the sum n equals 1 to infinity of AR to the n minus 1. And we said this is equal to A over 1 minus R whenever the absolute value of R is less than 1. And we said this series diverges. So this is convergent. And it's divergent whenever the absolute value of R is greater than or equal to 1. Okay, so that was the first test. The second test we looked at was the telescoping series. And they had a form. So I can't give you all the form, what the possible forms would look like, but we did have one on the exam, and that was the sum of n plus 1 minus 1 over n plus 3. And for this one, I told you to find the nth partial sum, and then you actually can sum the series. It becomes the limit as n approaches infinity of the nth partial sum. So recognizing it's a telescoping series, showing that it converges, and then basically drawing the conclusion that it's convergent. Then we looked at the integral test. There were some specific conditions there. The function an we wrote as f of n. We said f of x was continuous and decreasing. And then we said the sum n equal to some number to infinity of a sub n, and the integral from that number to infinity of f of x dx both converge or diverge. Okay. Then we looked at P-series tests. Oh, I think we did the nth test of divergence. I think I skipped that one. The nth term test of divergence. So we have the summation n equals 1 to infinity of an. Okay, so we know for this test, if an does not go to 0, then the series diverges. Okay, so then this is actually number 4. And then this P series is actually number 5. It also has a form, it looks like the summation n equals 1 to infinity, 1 over n to the p. And we say this converges if p is greater than 1 and it diverges 0 between p between 0 and up to equal 1. Okay. All right, so those were the tests that we've shown so far. Are there any questions about those exams before I go forward? I mean, not those exams, those tests, before I go any further? Okay. Hearing none, we're going to go to the comparison test. Okay, so the first test we're going to do is the direct comparison test. So I actually just want to, there are 2 comparison tests. I like to write them separately. Okay, so the direct comparison test. So let's suppose we have 2 series. We have the summation an and the summation of bn. Okay, and these are series such that 0 is less than or equal to an is less than or equal to bn. All right. After sum n. Okay, so these series, they all have positive terms, and I can show that the an is always less than or equal to the bn. So 2 things are true. 1, if the bigger series converges, then the smaller one has to. So if the summation n equals 1 to infinity of bn converges, then the summation n equal 1 to infinity of an has to converge as well. Okay, now likewise, if the smaller series is divergent, that means it just sits so big I can't figure out what the number is, then obviously the one bigger than that also has to diverge. So if the summation n equals 1 to infinity of the series AN if that one diverges, then the bigger one diverges as well. And this is a great test because I can use this test on series that seem like they can be difficult if I can just compare them to another series. Okay, so let's take, for example, this series. So the first example is the summation n equals 2 to infinity of 1 over n minus 1. Okay, for obvious reasons, I cannot start this series at n equals 1, so it starts at n equals 2. Now, as n gets very, 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 very large, n minus 1, well, does that 1 really matter? If you have $2 trillion, are you worried about the $1? Maybe you are, but it's not as significant because $2 trillion and $2 trillion minus 1 looks about the same. Okay, so I can say that this series to me kind of starts to look like 1 over n if n is very large. So it kind of looks like the harmonic series. So my guess for comparing would be the harmonic series. All right, so I guess, can we compare to the harmonic series? And the harmonic series is the summation n equals 1 to infinity of 1 over n. And actually, this series just has one term off, actually, so it's not that different. Okay, in fact, it pretty much is the same series where I start 1 at 2 with n minus 1, I start 1 at 1. But let's compare. So how do we compare these series? So we need to be able to show that either it's less than something that converges or greater than something that diverges. Now, I already know that the harmonic series diverges. We proved that the other day. So let's look at this. So we can start with n minus 1. Well, that is less than n. So therefore, 1 over n minus 1 is bigger than 1 over n. Okay, so now I have here that 1 over n is less than 1 over n minus 1. All right, so we have this condition up top that says we have a an less than a bn, so we're good. Now we know that the summation n equals 1 to infinity of, actually we can even start this one at 2. Of 1 over n is going to be less than the sum n equals 2 to infinity of 1 over n minus 1. Well, this series over here, this diverges. So that implies this one also diverges because it's bigger than a divergent series. Okay, so when I'm writing this up, I'm going to be able to show that I'm going to use the comparison test, the direct comparison test, because I am directly comparing one series with another. And in doing so, I can show that the one series I'm looking at is bigger than the harmonic series. The harmonic series diverges, therefore the second series also diverges. Okay, example 2. So let's look at the sum n equals 1 to infinity of 1 over n squared plus 6. Okay, well, I could go through and try to do some integral form with this. I know that's a little bit difficult, but we could do it. We could actually show that this works with an integral. But right now I'm trying to do the comparison test. So again, as n gets very, very large, n squared plus,
Yeah.
n,
Yeah. Yeah.
their question? Oh, let me just go back up here and just put that n minus 1 looks a lot like, okay. N
Hey, what are you
squared
doing?
plus,
That's loud.
it looks a lot like n squared. So they kind of look a lot alike when n is really, 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 really big. So let's see if I can look at the comparison between these two. Well, if I compare, this then means that this series, the summation n equals 1 to infinity of 1 over n squared plus 6, kind of looks like the summation n equals 1 to infinity of 1 over n squared for large n. Because n squared plus 6 kind of looks like n squared, so 1 over n squared plus 6 is going to kind of look like 1 over n squared. Okay, so this is the series. So this is the series I'm going to compare it to. All right. So I'm going to get n squared plus 6. This is bigger than n squared. So therefore 1 over n squared plus 6 is less than 1 over n squared. So now I can identify that this is going to be my AN and this is going to be my BN. Okay, now what do I know about the summation BN? Well, the summation n equals 1 to infinity of BN is the summation n equals 1 to infinity of 1 over n squared. Now I can identify that right away. That is a P series where P is equal to 2. So by the P series test, summation n equals 1 to infinity of 1 over n squared converges. Aha. Okay. So now we get the summation n equals 1 to infinity of 1 over n squared plus 6 is going to be less than the summation n equal 1 to infinity of 1 over n squared. Now this series converges. So therefore, it's going to imply that this series converges. All right, so if I'm larger than something that diverges, I diverge. If I'm smaller than something that converges, I will converge. Okay. Here's another example. This is a tough one. Okay, it's a tough one. This is the summation n equals 1 to infinity of 1 over n factorial. So as I write this out, actually, I'm going to start it at 0. So I write it out, I'm going to get 1 over 0 factorial. That's going to be 1. 1 over 1 factorial. That's also, wait a minute. I'm going to start it off at 1. I could start it off at 0, but for purposes of this discussion, I'm going to start it off there. So this is now 1 over 2 factorial, which is 2, plus 1 over 3 factorial, which is 6, plus 1 over 4 factorial, which is 24, plus 1 over 5 factorial, which is 1 over 120, plus ... So this is what 1 over n squared factorial looks like. I clearly can't use the nth term test because the nth term test is going to tell me that the nth term goes to 0, and so that's inconclusive. When I get that an goes to 0, that's inconclusive. So what can I do about this series? Well, I can compare it to something that has things in the denominator. So one of the series that we looked at is this series where we had 1 plus a half plus a fourth plus an eighth plus 1 over 16 plus ... Okay, so as I can see, this 1 is less than 1. I'm sorry, 1 equals 1. 1/2 equals a half. But the 1/6 is certainly less than 1/4. And the 1 over 24 is certainly less than 1/8. And then the 1 over 120 is certainly less than 1 over 16. So I can now say that as I write this out, 1 plus 1 over 2 factorial plus 1 over 3 factorial plus 1 over 4 factorial plus ... is going to be less than, well, the 1 and the 1/2 we said part were equal, but the 1 over 3 factorial is less than 1/4, and the 1 over 4 factorial is less than 1/8 plus ... Okay, so now this is the sum n equals 1 to infinity of 1 over n factorial. And that's less than the sum n equals 1 to infinity of 1/2 to the n minus 1. Now, what do you know about the series n equals 1 to infinity of 1/2 to the n minus 1? What do I know about that series? Any help here? Anybody there? Does anybody recognize the form of this series? It has a special form.
You mean
Is it
like it's
geometric?
yeah, I was gonna say it's a
Geometric series, very good.
Yeah.
And what do you know about R? What is R? In this
R
geometric, what's
it
that?
would be 1/2.
R is 1/2, excellent. So what do I know about this series then?
It converges because R is less than 1.
It converges, okay, because the absolute value of 1/2 is less than 1. Great, so therefore it implies that this series also converges. Okay, so that is the comparison test. All right. Okay, so the second test is the limit comparison test. Now, this is one of my favorites. I don't know why, but it is one of my absolute favorites. And it has several parts. So the first part of the limit comparison test is the easiest part. Again, it's just like the other one. So now we have, let's suppose summation AN and summation BN are series with positive terms. So AN and BN are both greater than 0. For all n after some number n. Okay, then these are our conclusions of this theorem. If the limit as n approaches infinity of AN divided by BN is equal to L, again, this is going to be positive because AN and BN, then summation AN and summation BN either both converge or both diverge. Number 2, if the limit as n approaches infinity of AN over BN is equal to 0, and the summation BN converges, then summation AN converges. And the last part, if the limit as n approaches infinity of AN over BN is infinity, and summation AN diverges, then summation BN diverges as well. Actually, that has to be summation BN. Then summation AN diverges. Now, I like this test better than the other one because I don't always have to try to figure out if I can find a series that's bigger than the one that diverges or less than one that converges. This one, I just need a series that kind of looks like it. So here are some examples. Number 1. So the summation n equals 1 to infinity of n plus 1. I've never seen it do that before. It like erased half my words. over okay. All righty. Now, if I look at this series, I'll need to think about what this thing looks like when n gets really, 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 really large. So when n gets really, really large, the most dominating terms are the n squared in the denominator. Oops. The n squared in the denominator and the n in the numerator are the most dominating terms. So for n large, this kind of looks like the summation of n squared of n over n squared of 1 over n. So it kind of looks like that. Okay. All right. Well, let's see if we can use that series. All right. So here an is n plus 1 over n squared plus 2n. And bn, I'm going to use 1 over n. Okay, only because when n gets really, really, really large, that's kind of what this series is resembling. All right. So now what I need to look at is the limit as n approaches infinity of an divided by bn. So that is the limit as n approaches infinity. An is n plus 1 over n squared plus 2n. And bn is 1 over n. So now we know when we divide by a fraction, we multiply by its reciprocal. We've been doing that for years. So that's the limit as n approaches infinity. So now I'm going to get n plus 1 over n squared plus 2n, and then that's going to be times n. So now I get the limit as n approaches infinity. So now I'm going to get, well, we can pull an n out here. So I have n plus 1, and then over in the denominator, I'm going to pull out an n. And so that's going to give me n plus 2, and then n over n. Those two are going to divide out. And so now I just get the limit as n approaches infinity of n plus 1 over n plus 2. And I'm hoping that you can see that limit is 1. Limit as n approaches infinity, divide everything by n. So I'm going to get 1 plus 1 over n. And then I'm going to get 1 plus 2 over n. So I'm going to get 1 over 1. That limit is 1. All I have to do is get a finite number. It doesn't have to be any number in particular. It could be 6, it could be 4. It just needs to be a fixed number. So therefore, since the summation n equals 1 to infinity of 1 over n diverges by the limit comparison test, implies the summation n equals 1 to infinity of n plus 1 over n squared plus 2n also diverges. Okay. Number 2. summation n equals 1 to infinity of n squared plus 4 over n to the 4th plus 2. Okay, anybody have an idea of what I might want to use as my series that I want to compare this to? Again, I want you to go through and kind of think, what does this thing look like as n gets really, really, really large? What does it look like for n large? So when n gets very, very large, my n to the 4th is way bigger than 2, and my n squared is way bigger than 4. So this looks like n squared over n to the 4th. So it kind of looks like 1 over n squared. So let's use that. So an is going to be n squared plus 4 over n to the 4th plus 2, and bn is 1 over n squared. Okay. So now we get the limit as n approaches infinity of an over bn. So therefore, I'm going to take n squared plus 4 over n to the 4th plus 2. And I'm going to divide by 1 over n squared, which means I'm going to multiply by n squared. Okay. So now I get the limit as n approaches infinity. So now I'm going to get n to the 4th plus 4n squared divided by n to the 4th plus 2. So that's the limit as n approaches infinity. Again, you can use L'Hopital's rule 4 times. Wait a minute. 1, 2, 3. 4 times if you wish. Okay. Or you can divide everything through by n to the 4th. Two over n to the 4th. And that limit is 1. So since summation n equals 1 to infinity of 1 over n squared converges by the limit comparison test, the summation n equals 1 to infinity of our original problem, which was n squared plus 4 over n to the 4th plus 2, also converges. Okay. All right, some of these can get pretty hard. All right. So here's one. N equals 1 to infinity of 1 plus n times the natural log of n divided by n squared plus 5. Okay, so let's think about this. When n gets for very large n, the most dominating term in the numerator is n times the natural log of n. And in the denominator is n squared. Okay, not worried too much about the 1 and the 5. So that kind of looks like the natural log of n over n. And as n gets really big, the n dominates the natural log of n. So this kind of looks like just something over n. So this is a guess. All right, I'm guessing. I'm trying to find something it might look like. And I know that summation 1 over n diverges. So since I know that, if I get this to work out, I'll be very happy. So I'm gonna let an be 1 plus n natural log of n divided by n squared plus 5. And I'm gonna let bn be 1 over n. Okay. So now I'm going to do the limit as n approaches infinity of an over bn. That's the limit as n approaches infinity. I'm going to get 1 plus n natural log of n divided by n squared plus 5. And I'm going to divide by 1 over n, which means I'm going to multiply by n. So this now looks like the limit as n approaches infinity. So now I'm going to have n plus, I'm going to have n squared natural log of n divided by n squared plus 5. So now let's divide everything through by n squared. So I get the limit as n approaches infinity. Actually, yeah, if I divide by n squared, I guess let's keep going. So I'm going to get 1 over n plus the natural log of n divided by, this is supposed to work. 1 plus 5 over n squared. And that limit's coming out to be infinity. Oh, yes. Okay, so this is the case back here. If the summation, if this is case 3, if the limit as n approaches infinity of an over bn is equal to infinity and summation bn diverges, then summation an diverges. Okay. So that equals infinity, and the summation n equals 1 to infinity of 1 over n diverges. So by the limit comparison test, the summation n equals 1 to infinity of the original problem, which is 1 plus n natural log of n over n squared plus 5 also diverges. Okay, so in each one of these, here, I wasn't specific, but in each one, you need to say by the limit comparison test. And this one by the limit comparison test. I think in the other ones we used, yes, this is the direct comparison test. This one was also the direct comparison test. And this one was the direct comparison test. Okay, so you have seen both the direct comparison test and the limit comparison test. Trying to get to the last answer for anybody who needed to copy it. Okay, and we will pick up here on tomorrow.
Have a good day.
Okay, any questions? Any questions?
Never mind.
Okay, thank you very much.
Have a good one.
You too.